So, hello everyone. My name is Darrin Young. I am one of the professors with the Electrical and Computing Engineering Department here at the University of Utah. I direct a research lab I call a Wireless Microsystem Laboratory. And, my email is darrin.young at the utah.edu. If you are ever interested, in my research work, feel free to shoot me an email directly. John, could you go to the next slide? All right, thank you. So let me just give you a quick kind of a rundown of my research lab by telling you the focus of my research lab. My research work mainly focusing on integrating advanced sensors, actuators, and a low power mixed signal integrated circuits at the system level to achieve autonomous sensing and wireless communication capability for critical applications. So I'm kind of come from a different side of electrical engineering, not so much on optics, materials, or, you know, things that you have seen up to this point. I came from semiconductor sensors, actuators, and IC designs. And specifically, when you look at the, critical application, you may wonder, what is critical application, right? You can define critical applications in many different ways. The way I define critical applications, at least for my interest in my lab, is, those applications require small size, lightweight, low power dissipation, and often, for application that we call a batteryless operation, and also require limited wiring access, such as biomedical implants, wearable sensing, personal navigation, environmental monitoring, as well as industrial sensing applications. John, could you go to the next slide?
Yep.
Yeah, thank you. Yeah, so this slide shows, well, this slide, the next slide, I have two more remaining slides, kind of give you a picture of the projects that either have been completed in my research lab, by my PhD students or ongoing projects. The very top one shows that, we worked on using micro electromechanical sensors coupled with, 2mm by 2mm low power circuits, combine them together, put inside your, into middle ear, not necessarily your middle ear. For example, a deaf person's middle ear to build an implantable microphone. And the second one from the top is a wireless implantable EMG sensors that we can tap off the EMG signal from the muscle in the residual limb, use that to control intelligent prosthetic limb operation. And the third one from the top is a wireless blood pressure sensor. And also in this picture, you can see that in the left side of the system, we have a little tiny chip that does the pressure sensing, as well as charging up a implantable battery surrounded by ferrites, with coils that can be implanted under the mucosal layer of a person. For example, a patient that suffers from urinary incontinence, to measure its blood pressure. And the last picture down there is a very interesting project, actually. One of my PhD students worked on using micro electromechanical sensors, pressure sensors, with his own custom designed CMOS low power circuits, put them together, build a fully functional device that can be put inside a live laboratory mouse that can be freely running inside a cage without any wire attached to it. And there's no battery inside that mouse. We're relying on, radio frequency power transfer from bottom of the cage to a power receiving device that's built as a part of the system inside the animal's body to sense its real-time blood pressure information. John, could you go to the next slide?
Yep.
Yeah, this is my last slide showing some of the ongoing research project in my lab currently. On the very top, we have built something called a small shoe-based personal navigation system without GPS. You probably can see from the upper hand left corner, there's a very flexible, tactile sensor array that one of my PhD students built, coupled with a CMOS chip. We put these devices together with, other sensors such as IMU sensors, accelerometers, gyroscope, all inside a shoe. When a person wears this type of smart shoe, he or she can walk around in the park or in the city without GPS signal. And we have demonstrated performance such as, one of my graduate students walked in a park called the Liberty Park in Salt Lake City, over 3,000 meters. And the accuracy, let's say that the position air is no more than 5.5 meters. In the middle is a implantable glucose sensor. Due to the time limitation, I won't get into the detail. You can see, one of my graduate students wearing this nice clean blue glove, holding that a prototype device. And on the right side of it, it is a CMOS chip that we designed. So I came from the circuit design background. And the chip has a 3 millimeter by 3 millimeter. More specifically, I think you can see maybe 3.3 by 3.3. But we're only using a small area, in the middle of that chip. It's about 1 millimeter by 1 millimeter, containing all the low power circuitry that is needed to receive power from outside the body, does the glucose sensing, take the data, digitize it, and transmit from inside the body to outside the body. At the bottom, it's another ongoing research project in my research lab. It's called wearable skin patch, health monitoring. It's very similar to, Professor Ben showed earlier, right? Is we're building something called a flexible skin patch that coupled with a low power CMOS chip that can detect real-time blood pressure signals, sort of indicating irregular heartbeats. And our demonstrated accuracy is, within 99% compared to ECG signals. So this gives you a kind of a high level picture of what type of research is going on in my lab. I'm mainly focusing on sensors, low power circuits for specific applications. I'm always looking for highly motivated students. If you are interested in this type of area, feel free to contact me. Thank you.